Good afternoon, everyone. My name is Pankaj Rajak. I am a postdoctoral appointee at Argonne National Lab. And today I'm going to talk about porting NAQMD kernel to GPU via OpenMP Offload. Let me give a first outline of my talk. We will give a brief overview of normal adiabatic quantum molecular dynamics simulation NAQMD, followed by code optimization and GPU offload of the most expensive kernel of NAQMD. And finally, we will talk about the performance of NAQMD kernel on Intel Gen 9 GPU. Here I would like to emphasize that our Intel Gen 9 results are very preliminary right now, and we have done that only on a very small problem size. Okay, let me give first a brief overview of QXMD. QXMD is a simulation engine for quantum molecular dynamics, or as we call it, QMD. In QMD, we followed a trajectory of atoms to study various materials properties, where interatomic forces between atoms are computed using first principles in the framework of density functional theory. QXMD also has capabilities to do have multiple extensions, like to do non-adiabatic quantum molecular dynamics or NAQMD and multi-scale shock simulation. Here we are showing two movies which of a simulations that we have done in our QXMD simulation engine. The left movie shows a rapid transfer of photoexcited electron from a photo antenna to a zinc propylene core in light harvesting systems, while the right movie shows charge separation of photoexcited electrons and holes in a rubrine C60 solar shell. Okay, the big topic of our talk is like NAQMD optimization. So here the main focus is the optimization and GPU offload of NAQMD section of the QXMD software. Upon examination, we see that the most computationally expensive kernel of NAQMD is the LFT calculation, or we say it as a local field dynamics. The local field dynamics solve main electron dynamics in the framework of real-time density functional theory using local pseudopotential and local gradient exchange correlation potential. Where the input to the LFT is the potential function and it returns electron density. Since QXMD is written in Fortran, for GPU offloading, we have developed a LFT mini app in C++ and integrated it with the Fortran QXMD software, where this C++ mini app gets potential field as the input from the QXMD and computes electron density and returns this electron density back to the QXMD function. The yellow highlighted section shows the timing of the initial LFT C++ mini app, where we observe that the most computationally expensive function in LFT are electron and field dynamic solvers. Okay. We first looked at the function electron field solver, and our objective here was to refactor this function first and then offload it to GPU. The highlighted box shows the original electron field solver code. At high level, we see that this function uses 4 nested loops, and the objective of this function is to update the value of this 5-dimensional array PSI. Also, some of the things which you observe here is that the variables like EL does not depend on any of the loop indices. So at the very first thing, what we can do here is to cache these variables ALI separately. So here we show this updated code with this AL variable cached outside. Second, now looking at the computational pattern during the update of PSI, we see that it uses a temporary multidimensional variable WRK to first store the results before updating PSI. Also, this code has a very inefficient memory access loop structure. For example, the dimension n along which PSI is updated is in the outermost loop. Thus, by loop reordering, we should be able to optimize this function and get rid of the temporary variable WRK. So the very first thing which we did, like to get better memory usage and data locality, we changed the loop ordering of the code. Basically, what we did, like to get a better data layout, is changed by moving the dimension n of PSI from the outermost to the innermost dimension. Similarly, the loop structure is also moved. Similarly, the loop structure is also moved to the innermost loop n. Like initially the n was the outermost, now it's the innermost loop. By doing this, we are able to get a better memory usage, data locality, and vectorization. The above code still uses a temporary variable WRK. To get rid of this temporary variable, we need to look at the computational pattern in detail of the innermost function. That means along this I, J, and K dimensions. Okay. Now in this slides, we talk about this I, J, K loops. This represents a three-dimensional grid point, and here the computation is basically along the X dimension. By plane. For example, here the computation of the grid point on the blue planes depends on the green planes as highlighted in the in this green box. Thus, the loop I has to be sequential. Thus, also that means instead of saving the result first into this multidimensional temporary variable before overwriting PSI, we can save the old value of PSI separately, which only requires a vector of size nr. And by doing that, we should be able to update PSI in place. Also, the other thing we observe here is that this last dimension PSI is basically a complex involves complex operation, where W0 is basically a real part of the complex operation and W1 is the imaginary part of the complex operation. So we can also leverage some complex data definition. This shows the updated code where we saw that the initially where the previous value of PSI is saved in PSI old. First we save along the 0 dimension, and inside the loop before updating PSI, we save the PSI. We first update the PSI old and then update the PSI. Similarly, as I mentioned, because the code has this lot of complex operation, so we also change PSI and PSI old from multi-dimensionality to a 1D complex vector. Now this code is much simpler, and the multi-dimensional array involving complex operation are converted to one complex variable, which is now easy to offload to GPU. Okay, now to offload this function into GPU, we have used hierarchical parallelism. The reason for this is as follows. We have some loop indices that are in parallel and some are sequential. For example, let's take the innermost loop indices n, which corresponds to different orbitals, and the update of these orbitals are independent to each other. Thus, the innermost parallel can be done using OMP parallel. As I explained before, the IJK represents three-dimensional direction, and the computation here is plane by plane. When the plane is concurrent and in between planes is dependent. Thus, in summary, we have used hierarchical parallelism here to optimize this function, where the coarse-grained parallelism on the outermost loop J and K, and using OMP team distribute, and the fine-grained parallelism on the innermost loop on N using OMP parallel. This shows the updated timing of this of the electron field solver code after the GPU offload, and we see a significant increase in timing from 92 to 1.4. This timing was done on Intel, done on IBM NVIDIA machine. Okay, now let's look at the next function, which is the field dynamic solver. At high level, this function contains multiple loop sections where each loop updates the individual point of a 40 grid VH. For example, here the dimension VH1 is updated using the value of dimension VH2, and similarly the VH0 is updated in VH1. And we can observe that this computation pattern is much simpler than the previous case of electron solver, field solver, which has a data dependency. Due to the independence between the computation of individual grid point of this VH, we are able to use flat parallelism to opt for GPU offload its code. And since also to minimize the data movement between host to device, we have pre-allocated VH on the device directly. Okay, this time shows the timing of this field prof offloading, and we see a significant drop from 200 to 100 second. However, looking at a GPU activity shows that the host side timing is still larger than the kernel time, which means kernel launch overhead is significant. Hence, to reduce the kernel launch significant, we tried asynchronous offload of these loops. Here, the idea, this is updated code with asynchronous update. Here, the idea is that to reduce the kernel launch overhead, we have to leverage target no wait. In this way, there is no need for the GPU synchronization at the end of each offload region. The purpose of asynchronous update is to launch as much kernel as possible. Well, however, this could lead to a data race as all these kernels reads and writes this VH variable. To reduce to resolve this issue, we add a dependency clause between the GPU task and the variant by adding synchronization construct. And now we see that after the update, the timing has reduced further.
Pankaj, can you quickly wrap up?
Yeah, I can. Okay. So now let me show the Intel Roofline analysis of these three codes on Intel Gen and GPU. This is the original Roofline analysis, the original LFT code, and we see that it is memory bound and has a very low self-performance performance. Now this shows the after the code refactoring and vectorization, and we show that the Roofline G-flop has went up from 2 to 6.5, and the data point in the plots have moved closer to the Roofline. This happened because of better data quality and vectorization of the code. And finally, this is the Roofline analysis of the electron field solver offload to the code, and we see a further increase in the self performance from 6 to 11.4. This shows the current slide shows the benchmark result of the different offloads between serial code offload of the electron field solver and the field propagation solver. One of the things, as we are talking about, which is key to observe that since the synchronization construct in the field propagation has this extra overhead, that's why this has a very high time. It has a very low throughput. And finally, to summarize my talk, we refactored the CP code with vector-friendly algorithms, changed data alert for better vectorization and data locality. GPU offload is achieved here by hierarchical parallelism. We reduce data movement by pre-allocation between device and host, and leverage asynchronous upload to reduce runtime cost. Thank you.